Hey, here's my project I'm really happy about building, and I hope it's going to work out and turn out great. And I hope everyone that sees it will like it and will build it themselves. It's called an adjustable circuit breaker. This is unique. No, I haven't found anyone on the internet that had a circuit like this. I found one on the internet to use a transformer in it, but basically what it was doing is measuring mains current for protecting devices on mains current. I wanted a circuit breaker that could protect devices on low voltage stuff, such as homemade projects and stuff like that people would do that usually are low voltage, like computerized stuff and digital stuff like that. Well, this is what this is what I'm talking about, and this is what we're gonna use. A adjustable circuit breaker just for that. What we got here is we got our resistor here. This is our current to voltage converting resistor. It does Ohm's law on it, because Ohm's law states that a voltage across the resistor equals current times resistance. It's 1 ohm, so that makes the math real easy. Makes you don't have to do no math on it at all on the voltage output. You get better results if you get a smaller resistance, because you get less resistance in the way, then your device will work better. But the thing is, you do it that way, you're going to have to do some math on it, and it may take time, and then before you know it, your device is broke. So that's why I chose a 1 ohm resistor over the other ones that we could have used. Because I wanted to use my meter, my one of these panel mount meters I bought from All Electronics. All this comes from All Electronics. The pot did, the circuit board, the panel meter, and resistor did too. This resistor here. All the resistors, all on there come from it. This resistor here, there's about, how many did I say? There was about one, two, yeah, 3 resistors on there. If you're not including the variable one and the and what you call the current sense resistor, or what I like to call the current to voltage converter. Because that's what it's basically like doing. It's taking a current source and converting it to a voltage source by putting it over a resistor. Let's see, right now we got no current flowing, 5 volts. Now let's put it over 5 volts over a 12 ohm resistor. This tiny 12 ohm resistor at this resistor is 3. Hang on, my wire come off. It's 3 watts. See if I can set this, man. Yeah, we can still see. There we go. This is the wire that's come off the terminal. I'm gonna put sooner or later. There we go. Sooner or later, I'm gonna put in there put this in it in the case it's a thing for a road. It's gonna have this USB cord still. This USB cord was my mom's one she had for an old phone that the cat chewed on it and it broke it. You can probably see at the end of here that there's a few spots in it that look like teeth marks that the cat's teeth must have went through. But it didn't break the power part. It must have broke the end into the phone. And this cord here was not a regular USB cord, not like USB 2.0, it's USB 3.0, but it works on the same USB 2.0 port. Because when I took the cord apart, there was more than 4 wires in it. And USB 2.0 lower have 4 wires only. There was about eight or 6 of them I saw in it. And some of them had foil around the twisted pair, and that looked weird. Anyway, enough to talk about that. You probably want to see it working in action to see how it works, to make sure I'm not lying. It does work. Right now we got a voltage on the meter. It says 2.26. Then that's our voltage across our setting for what the maximum current is, which is set by this blue resistor here, blue variable resistor here. That whatever voltage across it will be whatever current you're gonna trip at if it goes higher. Then you could get another meter to measure the current that you're drawing at right now. But the thing is, I decided not to do that to save money. Plus, also to make the project a lot bigger, make it harder to fit in tiny case like this. Because you have to have 2 panel meters instead of 1, and that'll make it real hard. So let's give it a go. If it trips, this white LED will light up, because that means that the normally open is now normally closed. And you'll see that there's no current flowing on this meter here. This is our current meter. 3, 2, 1. There we go. It's lit. Now I'm gonna hook it up to the 5. I'm gonna hook it up to the 5 volts and keep it on there. You can see it's still lit there. And if you hit the reset, that's something new. Oh, I see what it's doing. It's trying to switch over and it loses power. That's something new. It's still... But I don't think that's a problem when you have it on, as long as it loses power from it. It must be something to do with when you're trying to reset it and you got your load over it, then it'll oscillate. But you do not want to continue the oscillation too long, or else the relay could break. Because the relay here has small contacts in it and not that sturdy and stuff. And if it keeps going back and forth real fast, it could break. Those things could break off, and then you won't have no contact between them too. So I'll just take this out of there. I didn't know that, but it does work. Is what it's still. That's still a good thing to do. It still works. It's just that you gotta make sure that your loader. Now would be a good idea to have that there, so it does that, so that you didn't know that your load still does that. It still draws over that limit, and you can hit that, and you saw it just resetted it, and you didn't hear it oscillate. It oscillated because the draw on your one on that resistor there was drawing so much that it went over this range here. So the comparator tried to turn it off, and it didn't turn off. It stayed on. So it made pulses, just like it did in my simulator. In every circuit, it did that. It was going on and off, not doing what it's supposed to do. until I made one that had a latched relay circuit, like this one I have right here. Then it fixed it. But it must not do, it must oscillate if you had load on it constantly and hold the button down. Well, 2 days from now I might have it built, hopefully, but that might be next week or so. And the voltage comparator is very simple and easy to use, and there's no current that goes in or goes into the comparator's inputs and draws anything on it, which is so unique. Because I was learning about op amps on there, because the comparator is an op amp. It's made for comparing voltages more than being for op amps design. Well, that's it for now. I hope you enjoyed this video. Thanks for watching. Hope you like it. Before I decided to go and end this video, I decided to draw off a diagram and tell you how it works, and so you can build it on your own. So you have the schematic to do it. It's not that hard. You have a pot here, or a variable resistor. It goes to your non-inverting input or your plus input on the comparator. You set it to the variable resistor. It should be something that doesn't draw too much of a load on the power supply, but usually any kind of work the comparator is very sensitive, so it doesn't need, so it can work with very high resistance. So it can probably work for 1 meg, 500 kiloohms, 10 meg. You don't want to go down like say like 10 or 1 ohm, because then you'll be just loading up your power supply, and then could be not good for power supply, and it could not be good for the variable resistor. Anyway, another thing, we're using 5 volts here. On our 5 volts here, we hook it up to our comparator. The comparator can go to lower down to 5 volts. I could have probably choose a better one, but then I have to get a power adapter. So to make things cheap, I decided to use 5 volts and a USB cord. I'm gonna probably have one in the case. I'm gonna probably put a screw on there that comes out with the 5 volt wire, just in case if I want to run something off of the same power supply that's powering up the circuit breaker. Then I can do that. Right on the wiper connector, it goes to the positive input of the comparator. It goes to a voltmeter, DC voltmeter. I don't know I'm not for sure if you're probably having it to work with AC, you're gonna have to use some diode and some weird thing like that. Because there's probably a way of converting the DC current to a reading, AC current to a DC current reading. It's probably a diode or so, or a bridge rectifier or something like that. Thing is, it's gonna probably be way off on it, on its reading. Anyway, but this is just here the one off of power supplies for projects or low power stuff. Maybe like a CD player or a tape player that you're repairing on. You want to make sure it's not drawing over that much current that breaks. Then this here would be the ideal thing to do it with. Because what will happen is this comparator will do is it will compare the input pins, the positive input and negative input pins, these two here, see which one's greater. See which one's greater, then what I'll do is I'll output I'll put the correct clarity to be defined by those two. What I did is I looked at the wiring of what I got wired to, because first time I wired it, it was the opposite way. It was not doing it correctly because it was the opposite way. It was like the greater than was flipped over to maybe less than or so. So we had to put it around, turn the whole thing around. Anyway, another thing is on output you want to have two resistors going to it. Those two resistors are there so that just in case that it's open collector, your circuit will turn on, and if it does provide a positive voltage across it, it's not going to break your transistor. That's what the bottom resistor does. It protects the gate from breaking, and it works okay at 2K. You probably don't even put 10K there, because then there'll be 20K when it's on. And transistor try to saturate on. Try to switch on. 1K is good enough for switching. This diode that you see here is a protection diode. It protects the circuit protects the transistor and comparator from the reverse voltage that your coil of the relay may produce. It produces a spike that's in reverse. So it has so what that diode shorts it out on reverse, but doesn't short it out on forward. Or when it does, when the power supply to it, it's in reverse. But when that high voltage spike goes across it, it's in forward. I believe that's what it is. Because why else would you use a diode across there? I've seen a lot of circuits and known that I've been taught to use diodes across across a relay coil. The relay, you want it to be, make sure it's double pole, double throw, or you can have double pole single throw, except you won't be able to have a LED that shows this overload LED on there that turns on once it trips. If you have a double pole single throw. This is because you have to at least that, because this here turns this relay on. When this here goes down and hits that, current will flow, and then when this thing releases the current, this here, I forgot to put the switches in here. Hang on. The switches will go. We could put them like here. I put them in the negative line, but it shouldn't matter which one do it, as long as you put it in front of the power lines that go to the relay coil. So you could probably put in positive, and you could probably do it. We probably should put in probably right here, in between the ground there. That's probably where I put it. I think that's where I put it, because in the ground it was going to the coil and between the contacts. Also, this here probably cannot. I don't know how we'll do it. If we're gonna do for mains, I do not want to destroy my comparator circuit or blow it up and make it where it catches on fire or blow a fuse by trying to test something that runs on mains. Because not only that, my resistor can only handle like 50 watts. And there's a lot of stuff that draws over 50 watts on mains. And if it draws over that, it'll ruin that current sense resistor. It'll get hot. And not only that, to have it at the full power, when I was reading at all electronics, it says you have to mount it to a heat sink. And I don't know where I can get a heat sink for that resistor. So I'm just I'm probably not to worry about it with my projects. It's not going to be that high power. So it's probably okay to leave it without a heat sink. It probably will never heat up. And so that's why we're not gonna do it with mains. You can try it yourself if you wanted to. You're gonna probably have to use this. Well, if I was gonna do it, what I would do is put a bridge rectifier there and put the positive output, positive negative between your ground and negative, and your positive will go to the non-normally closed pin of the relay on the side that has your load hooked to. But the thing is, we got an issue. That voltage, it's gonna be bouncing around like that because it's alternating current without we rectified voltage without a filter capacitor. Without that filter capacitor, it's going to be bouncing around. You just have to figure out what kind of capacitor you have to put in it. And you don't want to put too much. We don't want to put too low capacitance so it doesn't hardly draw anything. That I don't know. You could probably use low capacitance, I bet, in it. Thing is, I've seen analog multimeters not have any capacitors in it, hardly any. Maybe none. But that might be because it's just made for that, for that peak, that bounce around voltage at 60 hertz. I'm not for sure. Not really, don't know how those meters are made. Hang on. Okay, now we're going to explain this in a few minutes why I have two resistors here. I had them to put this here because this bottom one here limits the current. That if this here was positive, because if this was positive, then this one would have no meaning because it would be bypassed. And it would flow through it, and then your transistor could draw too much current and could break. So to be safe, I recommend putting two resistors in series like that. When the top resistor does is acts like a pull-up resistor, then the bottom resistor acts like a in series current limiting resistor that goes in series with the base of our transistor. This is so that you can use a time transistor for powering your relay up, because the relays don't draw that much current. Thing is, computerized stuff on it, you might be lucky enough that you could win off the comparator. I've never tried that, but the thing is, I was gonna do it this way because I didn't know if it'll work off the comparator or not. I think you can. It's just that there's weird stuff I have to do that I'm not used to with it. Anyway, so I just did it this way. Anyway, right here we got our load and it connects to there. Now the positive, the negative, goes directly to ground of your load. And that means that's your ground of it. Then positive takes your voltage going into it, goes through it, As it come out through it, it goes into it. Positive going like that way into it. You can't put negative there. You put negative like that, you may break something. So it's very important to follow the polarity. So with my red and black speaker terminals, I could easily just take this easily know which one's positive, which one's negative. Because negative supplying the negative voltage across it could do something. Because let's take a look where it's going to see where it goes. If we're positive here, that means I'll go see a ground there. I have no idea. Maybe it might work and it might not. But I'm not going to take a chance of breaking it. And plus also it's made to have positive voltages on there, not negative. It may work with negative voltages, but the thing is, I don't know how well it. I never tried to use negative. All I've been using is positive. I'm going to keep it that way. We can always keep it that way. It doesn't matter. It does matter, but we'll keep it that way. It may not matter, but we'll keep it that way. The other side of this here, I drew some diagrams of the resistors and explained why I chose to do it that way. So this resistor, you see, you got this resistor here. Now let's say that the middle part's grounded. And this is the base. Down on the second resistor, the base goes to the base of our transistor, just like in that circuit there. And where the ground is where our comparator's output is. So let's say the output of the comparator was a ground. So what happened is that our 5 volts go to this resistor, go down out to the comparator's output, and go down to ground. Nothing will go to this resistor here. And what happens if you have nothing going to the base of a transistor? It's switched off. I had to do it this way. You could probably say do a simpler circuit, like use a PNP transistor, but I already ordered NPN at the time, and I don't want to have to go back there and reorder PNP. I should have probably did at the time, ordered both NPN and PNP. Because you put a PNP transistor there, you eliminate the need of 2 resistors. You only need 1. And it just goes directly to the output of the comparator, and then to the relay. The thing is, you probably have to swap those, swap the positive and negative inputs of the comparator, and you'll probably have to swap the the positive negative power pins on the relay that go to which pin goes to the transistor. Now let's say you have 5 volts in on both pins. Well, it'll go through there, but there'll be more current flowing because instead it's bypass this resistor. It doesn't matter whether it's on this resistor or not. This resistor can be unhooked, and they'll send power directly to the base and still turn it on. And they'll still be at full power. They'll probably what it'll do is it'll be a parallel resistance. With this parallel resistance in there, it'll have more power to it. It'll be greater current, a little bit greater, but not that much. About 1K, probably 1K at so many milliohms or so in series. Then right here, we got nothing on it, which is probably what our comparator is doing. With the nothing there, we got the voltage going through it, and it's not bypassed. Oh, we're not seeing it. Nothing on this one, on this side here. And then they're all bypassed right there. Not bypassed, it go through it. Well, this one has it bypassed because there's a 5 volt in the middle section. So it's like putting that resistor parallel with a with a milliohm resistor, because there has to be some resistance in it. Wires have resistances. Some have more than better resistances than others. But wires, they use them because they use less resistance. Usually that's what you need to have your stuff wired to, so power gets through. Anyway, the comparator I chose was an LM311H, and the H is the one that's in a metal can. When it's in a metal can, it's probably meant for better voltages than 5 volts. You could probably run it up to 36. I wonder if the chip gets even hot at 36. It may. And that might have been why they made a metal can one, so it could handle the heat and the voltage from it. But anyway, it works. If I never get high at all, because anyway, for the input pins to go real high, you gotta draw the same amount of voltage. Voltage must be equal to the current you're putting into it. Since we're using that, and I'm gonna go over that next. Why I chose 1 ohm resistor. Hang on, I'll get a piece of paper, a new one I've been drawing on. Okay. Resistors have an equation, Ohm's law, that states that voltage equals current times resistance, or you can call it V equals IR. I is current, R is resistance. Now, how do we make voltage equal, make something equal that reading as what we're measuring? You have to multiply it by 1. So what are we going to set to 1? Well, we can't set the current to 1 because it always be 1 amp. That's not useful. So what we'll do is set the resistance to 1. And that's low resistance. 5 volts, you get like 5 amps out of it, the max. Or if you want to computer stuff off of that, it needs like 10 or 20 amps or so off of that 5 volt rail. Yeah, you might have a problem measuring with that. And at 5 amps, at 5 volts, meters use less resistance because the less of the resistance, the less of voltage output you get to your resistor, putting that resistor on it. That's going to cost a resistor. It's because it multiplies it by a lesser value. So if we multiply it by more value, you get more voltage out of it. But the thing is, here's the catch. You cannot. Let's say, for example, if I have 10 volts, 10 ohms, not 10 ohms, let's say it's 1 ohm, and I'm drawing 5 amps, want to draw 5 amps, but my power supply is only 3.3 volts. it's not going to come out to be 5 volts on the other side, because it can't get 5 volts when there's not that enough being supplied. So it'll be a lot less. Probably make a higher value, and it'll probably be at the maximum as it can. Probably the 3.3 volts or so it'll measure across it. Maybe nothing. Might drop it and act like a dead short. I'm not for sure. Thing is, with these resistances, the less the resistance, the better measurement you'll get, and the better your circuit and project will work with it. But for these small circuit, these project ones where you're doing 555 timers or power supply with the LM317 and stuff like that, simple stuff like that, this 1 ohm shouldn't bother it. It shouldn't harm it, it shouldn't interfere with it, should not make it have problems. Even if I was using my, you can see over there in that wooden box, that's a power supply there, and it has 1 ohm as it's a shunt resistor to measure the current across your load that you're drawing on it. That there, that would be 2 ohms, but the 2 ohms ain't that bad either. Now if you talk about 10 or 20, maybe it'll be a little bit bad. So basically, if you make your current, your resistance 1, you'll get the same voltage as your current measurement, and that's why we call it a current to voltage converter. And this is why this is needed. It is because this is not a current regulator. There's no such thing, I believe, as a current regulator. Not a current regulator, I mean current comparator. There's a such thing as a voltage comparator, so that's why you have to convert it to a voltage. So it compares them. So the voltage on across this here, since we use a variable resistor with all 3 wires, that means you make it into a variable voltage divider. So then a voltage across it, you can adjust it. So this thing can be adjusted all the way up to 5 amps, but if thing is, can it handle 5 amps? Probably not. I bet the relay will break on 5 amps. Because the thing is, there's contacts in there, and if there's a lot of current on there, that metal can melt or break off when they tap each other for making contact. Especially in a small relay like I chose. That's probably why it was like $1.55 or so on all electronics. But the thing is, I chose it was because that it would fit in the chip socket, so it made it easier to mount to a board. Anyway, so basically your maximum current depends on the wattage of this and contact current, that maximum contact switching current that your relay can handle. Plus your voltages, the voltage you're supplying, the voltage that you supply doesn't go, that your amps will not go greater than that. Can't go greater than your voltage source. Of course, you can change your 1 ohm to maybe 100 milliohms. 100 milliohm resistor or something like that, and then you could probably get down to where it can measure really good current and then the voltage wouldn't have to matter being so high. You get more current out of it. What I'll bet happens, you'll probably get the maximum current that the thing can do without. You probably get the voltage will probably be as high as it goes, but then your current will probably be way less because it may be high. It'll probably be high, but the thing is, it'll probably be at the maximum it can supply. I feel like done talking about this, so now you know. Here, this is how you can build it. And you can buy this stuff from All Electronics. You can buy a board. You can buy the circuit board off there because it was a 300-point circuit board. The one with the breadboard that fit the breadboard pattern. Because that's what puts the relay on. Because the relay fits it into a chip socket, and that's what made it nice to use because it could fit in the chip socket. So, well, that's about it. I hope you enjoyed this video. Thanks for watching. Hope you like it.